We have already solved question 126 of the question paper 42 of 9701 chemistry of the examination series October-November 2024, and in this video we are going to solve questions 7 and 8. But before we start, let me tell you that if you want an access to an unlimited IGCSE or GCSE resources, then I have given a link in the description where you can go and get an access to an unlimited resources for revision, videos, notes, exams, exam tests, worksheets, past papers, everything in the link below. So just go ahead and download the app. So now starting with question 7, it is benzene reacts with chlorine gas to form chlorobenzene. Now this reaction can be described as a reaction between benzene molecule and the Cl plus ion, that is Cl plus ion. The Cl plus ions are formed by adding a suitable catalyst to the chlorine gas. Now give the name of the formula of the catalyst that can be used for this reaction, and the catalyst used is aluminium chloride. So here I have written the formula, but you can even write the name, that is aluminium chloride. In the B question, the mechanism of this reaction is shown here, and you can see that here is the mechanism shown where all the three diagrams, that is three benzene ions or molecules, you can say, which are used for forming the chlorobenzene from benzene. Now the A part, the first part of the B question, is the movement of a pair of electrons is represented by X in diagram 1. Now here you can see the diagram 1 where the movement of electron is presented by X here. Now state where this pair of electrons is before step 1 takes place. Now before step 1, now step 1 is this one, that is the movement of electron is happening. Now before the step 1 takes place, so where is this pair of electron? This pair of electron, you can say that this is present in the delocalized system of benzene. So we can write delocalized system of benzene. So this pair of electron, which we have denoted here by X, is present in the delocalized system of benzene, or even you can say pi bonding system of benzene. That is also acceptable. Now state where this pair of electron is after the step 1 has taken place. Now the step 1 is here, and we can see that the pair of electron which was donated by X has gone to Cl plus ion. So you can say that that pair of electron is used here to make a bond with Cl. Now where is this bond? This bond is CCl bond. So you can say that it is used in making CCl bond, that is carbon chlorine bond. So that is where the pair of electron is being used after step 1. The second part is the movement of another pair of electrons is presented by Y in the diagram 2. Now state where this pair of electron is before step 2 takes place, and state where this pair of electron is after step 2 takes place. So now let's see where is this Y before and after this step 2. Now here is the step 2, and you can say that the pair of electron is shown here, which is presented by Y here. So this pair of electron before the step 2 is the CH bond. You can say that it is the CH bond. So you can say that it is present in CH bond, that is carbon hydrogen bond. Now state where this pair of electron is after step 2. Now we can see here that this movement of electron with the arrow is shown. So obviously that pair of electron has shifted inside the benzene in the delocalized system back. So you can say that it is present in the delocalized system of benzene ring. So that has shifted back in the delocalized system, and the delocalized system has come back to its intact position. So C question is, there are 6 carbon atoms in diagram 2. State how many of these carbon atoms are sp hybridized, sp2 hybridized and sp3 hybridized. Now first let's understand what is sp, sp2 and sp3 hybridized of carbon. Now what in short I generally use to explain my student is that whenever we have an C triple bond C, this is an sp hybridized system or state of carbon, because that is how the bonds form because of the hybridization of s and p orbital. But if we have C double bond C, then it is sp2 hybridization, and when we have C single bond C, then it is sp3 hybridization. And now let's have a look at the diagram 2 here. Okay, diagram 2 is here. Let me rub out everything to understand the system. Now understand what is the question. Now they have asked about the 6 carbon atoms of the benzene in diagram 2. So here is diagram 2, and these are the 6 carbon atoms of the benzene ring about which they have been asking. Now they are asking that how many are in the sp hybridization. Now you can see that there are no carbon with C triple bond C. So our answer for sp hybridization is 0. But now how many carbon atoms are having C double bond C, and that is for sp2 hybridization. Now if we start counting here, this carbon, 2 carbon are having the double bond because this ring denotes the double bond. So here is 1, 2, 3, 4 and 5 carbon, because this double bond ring is covering the 5 carbon of the benzene ring. So for C double bond C, we can say that there are 5 carbon involved in the double bond in the delocalized system, also they have sp2 hybridization. Now this is the only carbon which is having the single bonds, and so that is called sp3 hybridization, that is 1. So let's note it down here that sp hybridized carbon are 0. There are 5 carbon with sp2 hybridization, and there is 1 carbon with sp3 hybridization in diagram 2. Okay, let's go ahead. In the D sub question, complete the equation for this reaction between the benzene and the chlorine. So here if we add benzene is given here C6H6, and we are adding chlorine here. So we can complete by replacing one of the hydrogen with chlorine. So this is C6H5Cl. One of the hydrogen is replaced by chlorine. So one hydrogen is replaced, that goes and bonds with the remaining carbon atom left. So after the 2 chlorine of the chlorine molecule, 1 chlorine bonds with the benzene, and the second chlorine is bonding with the hydrogen which was displaced or substituted by chlorine. So this is a complete reaction. Now E is the mechanism of this reaction is electrophilic substitution reaction. Complete the following sentence. Write the formulae in the gaps provided. So here are the gaps we have to fill in the formulae. Now during this reaction, the electrophile is Cl plus. Cl plus is, if you recall the definition of electrophile, they are the one which accepts electron pair, and so they are supposed to be positively charged, and so in this reaction electrophile is Cl plus. And a dash atom in benzene is substituted by a dash atom. Now what atom is substituted by what atom in benzene? We know hydrogen atom in benzene is substituted by chlorine atom. So write the formulae in the gaps provided. So these are the formulae we have written for each and every gaps. Okay. F question is, chloroethane reacts with NaOH. Chlorobenzene does not. Now what is the difference here? We have an aliphatic chain of ethane with 2 carbon. Chloroethane reacts with NaOH, but chlorobenzene does not. Now name the mechanism of reaction that chloroethane undergoes with NaOH, that is sodium hydroxide aqueous, and identify the major organic product that is formed here. To understand all this and to get its answer, we need to understand that if chloroethane, that is C2H5Cl, reacts with NaOH, then we get ethanol, that is C2H5OH we get. Now OH is what? We are replacing chlorine with the OH, that is hydroxide of sodium hydroxide aqueous, and we get NaCl as a byproduct. So now what is this? This is a substitution reaction, and in this it is a nucleophilic substitution reaction because the OH is a nucleophile, which is an electron pair donor. So the mechanism is a nucleophilic substitution reaction. Now the major organic product form, as I've already shown you, it is ethanol. So we can write ethanol here. It's clearly written, name the mechanism and identify the major product. So major product is ethanol, and that is also organic major product. Now the second part is explain the difference in the reactivity of chloroethane and chlorobenzene when treated with NaOH aqueous, that is aqueous sodium hydroxide. Now what is the major difference? In benzene we know there is a delocalized system of electron pairs, and what is happening is we need to substitute chlorine with the hydroxide if the reaction takes place. Now that is not easily possible if you say that the chlorobenzene is not reacting. So the only reason is that the lone pair of chlorine gets delocalized with the pi bonding system of benzene, Now you can write the same sentence in another words, is that the lone pair of chlorine overlaps with the pi bonding system of benzene. That also can be written, and because of that the CCl bond in benzene is stronger. And cannot be broken that easily. That's the reason that it is unreactive with aqueous sodium hydroxide, but chloroethane, the ethane part is electron donating and it will easily break. The CCl bond will easily break, and so it will react also easily. Now question 7 is over here. Let's go ahead with question 8. Question 8 is the amino acid serine, that is formula is given here, exists in two optically active forms. Now these optical isomers, isomer P and isomer Q, are shown in figure 8.1. So here are the two optical isomers of the amino acid given. The isomer P and isomer Q have identical physical and chemical properties, with the exception of two specific properties. One of these two properties is their differing effect on the plane polarized light. State the other property by which they differ. Now we know that the amino acids inside the any living being they are reaction specific, that is they react in a specific way only. So if they are optical isomers, the isomers are different, their biological specificity or the reaction will also be different, and that is how we can say that their biological reaction or their biological specific reaction will also differ. That is, you can, other word in biology they always say biological activity, but here we write biological specific reactivity differs here. Okay, the B question is the solution of a pure isomer P of a particular concentration rotates plane polarized light by 5 degrees in a clockwise direction. Describe how a solution of pure isomer Q of the same concentration affects the plane polarized light. Now we know that they are optically active but they are non-superimmersible. So what we can understand from this is that it will have the same reactivity or same effect, but only the direction is different. So here if it is written clockwise direction, the activity of the isomer Q will be anti-clockwise direction. So that's how we can write that it will rotate the plane polarized light by the same angle, that is 5 degrees, in an anti-clockwise direction. So that's the only difference. The difference is in the direction only, not the angle. The angle will remain same. So here is the C question. State another term in addition to the stereoisomers, optical isomers and non-superimposable mirror images, which can be used to describe this pair of chiral compounds isomer P and isomer Q. The only other word which is used for the same thing is enantiomers. It's called enantiomers. It means the same, but the term used is different. Okay. The D question is, give the term used to describe a mixture containing equal amounts of isomer P and isomer Q. So what is the term? The term used to describe a mixture containing equal amounts of isomer Q and isomer P means the concentration remains same in the mixture. And now that is called racemic. So racemic is the term used when they are mixed in equal amounts. So that's called racemic mixture. Racemic mixture. Okay. E question is, describe one way in which a single pure optical isomers of serine can be produced instead of making a mixture of isomers P and isomers Q. Now when we are making, now that's something very important in biology nowadays, that if we want to make a pure single isomer, we don't want the mixture of the two optical isomers as shown here, isomer P and isomer Q. Then what can be the method? The only method is either we use the starting material itself. If it has any chiral center, then the starting material itself can be chiral, or we can use a chiral catalyst. Now if chiral catalyst is used, it's going to make a specific product only. It won't make the mixture of two isomers. So we can write chiral catalyst is used to make a specific isomer. Now here is question F. Complete table 8.1 to describe the peaks seen in proton, that is NMR spectrum of these compound dissolved in D2O, that is heavy water. Now we need to understand that with heavy water, the OH and the NH proton both gets replaced by D and it won't show any peak in the proton NMR spectrum. So now use as many rows in table 8.1 as you need, leaving the other rows blank. So here so many rows are shown. Now what are we supposed to do? Let's go ahead and read the question again. It says table complete the table to describe the peaks seen in proton NMR spectrum of this compound. Now group responsible for the peak, name of splitting pattern shown by the peak and explanation for that splitting pattern. Now we need to understand that what is the whole structure, and then we can make out how many protons will give this proton NMR peak. Now as I said, the structure, I'll draw it here again, is HO, CH2, CH, NH2 and COOH. Now let me recolor all this. and show you that this is the proton which will not show the proton NMR peak. So what are we left with? We are left with CH2 peak and the CH peak only, which is going to show in the proton NMR peak. So in the first column where group responsible for the peak, we will write CH2 and CH, which will show the peak, and name the splitting pattern shown by peak. Now with CH2, that splitting pattern depends on how many protons are there in the neighboring carbon atom. Now this CH2 have only one carbon in the neighboring, because besides it, other sides we have OH group. So this carbon have only one proton. So 1 plus 1 peak is shown. So doublet peak is shown for CH2. And the reason is that there is one proton on adjacent carbon, one proton on adjacent carbon atom. That's what we are going to write. Now with CH, again on the other side we have NH and COH. There is no carbon carrying the proton directly. So there is again only one carbon carrying the proton. Now that carbon have two protons. So 2 plus 1 peak are shown. So now we have triplet splitting for that. The splitting is always the number of proton at the adjacent carbon plus 1. That will be the splitting of the proton. So here we have triplet splitting, and again we will write the same reason. There are two protons on the adjacent carbon atom. So that's why we will have triplet splitting of these carbons, of the protons. Let's see what is the next sub question. Proline is a naturally occurring amino acid. The skeletal formula of the proline is shown here. So here is the structure. State the number of peaks of carbon 13 NMR spectrum of proline. So here now understand, it is not proton NMR, it is carbon 13 NMR. Now let's count how many different types of carbon atoms are present in this compound. Now we can see here that the most of the carbon present are different, because we cannot draw any line of symmetry on the ring here. So there is one carbon atom here, second carbon atom, third, fourth and fifth. All the carbon atoms are different. It is not having any similar environment. And so that is the reason that all these 5 carbon will show a different peak. So the number of peaks of the same compound will be 5 for carbon 13 NMR. Okay, let's go ahead and see what is the next question. Glutamic acid is a naturally occurring amino acid. Again, the skeletal formula of the glutamic acid is shown. The isoelectric point of glutamic acid is pH 3. Now, what is an isoelectric point? Isoelectric point is where there is positive and negative charged ions present in an acid, but number of positive and negative remains same. That is, it occurs as electrically neutral compound at pH 3. At pH 3, it is neutral electrically, but if the pH change, it might be charged compound. That's what is meant by electric point. So electric point of glutamic acid is pH 3. Now a sample of glutamic acid is dissolved in a solution with pH 1. Now you can see that the pH is changed. It is pH 1. A strong alkali is then added until the pH of the mixture reaches pH 14. During this process, all the possible ionized forms of glutamic acid are present at different times depending on the pH of the solution. Complete the boxes below to show 4 different ionized forms of glutamic acid that are present at the stated pH values. Now here we have 3 at pH 1, at pH 3, at pH 9 and 14. So here is the structure. Now let's understand that what happens to the structure, what difference does it make when the pH is acidic or basic for it. Now if we compare, the isoelectric point is pH 3, that is for pH 1, and hydrogen ion will be donated because the pH is lower than the isoelectric point. So at pH 1, the hydrogen ion will be donated to the glutamic acid. That hydrogen ion reacts with the basic part of the glutamic acid, adding H plus here. So that makes NH3 plus on this part. So let's draw a structure making the remaining part similar. So starting with the OH part here, we are drawing it same, no difference. Then the remaining carbon atom are same again, the COOH, that is carboxylic group. But with the NH group, we will add one hydrogen and the positive charge because H plus is added to the basic part. Now as we know, at pH 3 it is isoelectric, so it should have one negative and one positive charge. So we can remove any one of the hydrogen from the structure. So if I'm writing H here, then the other side H can be removed and make it O minus, and the NH is again having an additional proton, making it a positive charge. So overall, with one negative and one positive, the overall charge is neutral. On the same way, you can remove even this proton and make one negative charge this side, then don't add negative charge on the other oxygen atom. That also can be done. That is also possible. Now at pH 9, one of the proton will be removed because that becomes basic for the environment of the amino acid, and that's why it loses one of the proton from the carboxylic part. So because of that, you can remove any one hydrogen from any of the OH. So I am removing just one hydrogen from one of the carboxylic part, and I'm drawing the remaining carbon atoms same. OH I'm writing as such with the other carboxylic part, and then the NH2 also remains same. So overall there is a negative charge because one of the proton is removed, that is the hydrogen ion is donated in the basic environment, you can say, and that's why overall charge is negative now. Now at pH 14, it is too basic for this glutamic acid amino acid, so it loses both the protons from the carboxylic part, and that's why you need to add two negative charges on both the carboxylic parts. So again O negative, the remaining carboxylic part, and the NH2, that is the basic part, remains the same with the basic pH, or you can say pH greater than the isoelectric point. So this is how you draw the structure. Remember, the pH which is below the isoelectric point, there we will add the hydrogen ion to the base part. If the pH is above the isoelectric point, then we will remove out the hydrogen ion, making the COO group negative. And this is how you draw the structure of amino acids at different pH when you know the isoelectric point. So I think now here the last question 8 also ends. I hope my explanation is very clear.